Swayam Prabha. Digital India. Educated India.
We will continue with the topic of Lagrange's equation, Hamilton's principle, application of Hamilton's principle and deriving Lagrange's equation of motion, and we will look at examples. The second example that I have is of a pendulum on a cart, supported from a cart, and this cart is connected by a spring to the wall as shown. It is an anchored, flexibly anchored cart. We would like to find out the equation or derive the equation of motion for this system, and we are going to use the Lagrange's equation of motion. The generalized coordinates, first and foremost we must identify the generalized coordinates, and generalized coordinates for this system are quite straightforward. We have looked at this example before. They are theta and x coordinate of the cart, theta of the pendulum and x coordinate of the cart. There are two generalized coordinates, therefore, we will have two equations of motion, and I have written out these two equations of motion. d dt of del L del generalized coordinate rate of the first generalized coordinate q dot minus del L del theta is equal to 0, and the second equation is for the x coordinate, d dt of del L del x dot minus del L del x equal to 0, and L, the Lagrangian, this is a mechanical system. Lagrangian is nothing but kinetic energy of the system minus potential energy of the system. Let us look at that expression. Kinetic energy of the system can be written as 1/2 the mass of the bob of the pendulum times velocities of the bob square plus 1/2 mass of the cart times velocity of the cart square. How do I find out the velocity of the bob? Here we have to use kinematics. I represent the position vector of the small mass, the bob, and it is represented in terms of x and theta, the generalized coordinates. I can always do that, that is the purpose of using generalized coordinates. I can find out the physical coordinates of the bob, and this is what it is. Rm is equals to x I cap plus L, length of the pendulum, times unit vector along the pendulum represented in the xy coordinates that I have shown in the figure. And I can derivate this, time derivate this position vector and find out the velocity of the bob, and velocity square is nothing but V m dot V m dot V m. So, velocity of m square is nothing but V m vector dot V m vector, and from there I obtain the velocity square of the bob, and when you simplify you get this expression. So, details are left to you to complete. Therefore, the kinetic energy can be rearranged in this form. The kinetic energy of the whole system can be rearranged in this form. You will notice that we have used the generalized coordinates and their rates. Now, the potential energy expression, we have potential energy because of the spring and we have potential energy because of the gravitational potential energy for the bob or the pendulum. The spring potential energy is half kx square, and with the datum fixed at the x axis the potential energy datum for the pendulum, we can write down the potential energy of the pendulum as minus mgl cosine theta, and the total potential energy is the sum of these two quantities. Now, the Lagrangian is kinetic minus the potential energy, kinetic energy of the system minus the potential energy of the system. So, here you have to be careful about the sign. With this Lagrangian and our equation of motion we have already written, we have to find out del L del theta dot. We have now two terms which involve theta dot. This is one term and this is one term. Therefore, we get two terms in del L del theta dot, and d dt of del L del theta dot. Now, you should be careful, because when we take time derivative, of course, here it is going to be double derivative, rest of the terms are constant, but the second term we will have a double derivative of x, and because theta is also a dynamical coordinate, theta is changing with time, therefore, we will have a third term here because of the time derivative of the second function. That is d dt, total time derivative of del L del q dot, and del L del q we have theta contributions from two terms, one is this, the other is this. Therefore, we can calculate del L del theta. Therefore, the equation of motion for the theta coordinate, this is d dt of del L del theta dot minus del L del theta is equals to 0, that gives us this equation, which you can simplify. You can simplify. We have the standard terms of the pendulum equation, and we have this additional term now. Now, the second equation of motion, which is for the which corresponds to the x coordinate, we have to calculate del L del x dot. Here I have calculated that there are two contributions, d dt of del L del x dot. Once again, the first term, when I derivate the first term, I will get a double derivative of x. When I time derivate the second term, we will have contributions from theta dot and cosine theta, and this is how it looks. And del L del x is only minus k x. Therefore, the equation of motion, in this case the equation of motion is d dt del L del x dot minus del L del x is equals to 0, and that gives us this equation of motion. We move to the next example, equation of motion of a simple pendulum on a uniformly rotating disc. Here in the figure you can see there is a disc on the circumference of which at a radius r, circumference of which we have pinned a pendulum, and the whole thing is moving in a plane, the plane of the screen, and the disc is rotating at a constant angular velocity capital omega. The system is in a uniform gravitational field. First, we need to identify the generalized coordinate. There is only one generalized coordinate, which is theta. We can find out the position of the bob given theta and of course time. The Lagrange's equation, therefore, there is only one Lagrange's equation, and that is corresponding to the generalized coordinate theta. The d dt of del L del theta dot minus del L del theta is 0. We have to write down the Lagrangian, which is kinetic energy minus potential energy of the system. Let us start with the kinetic energy. the bob is massive. So, that only contributes to the kinetic energy. We have to find out the position of the bob, the physical coordinates of the bob, which will be known in terms of theta and that angle omega t, which means in terms of time omega being a constant. This is the position vector of the bob. Therefore, I can derivate this to find out the velocity vector of the bob, and if I know the velocity vector, I can find out velocity square. Once I have velocity square, I have kinetic energy. So, this is the expression of kinetic energy. Secondly, we have to write down the potential energy. The potential energy contribution comes only from the bob, from the pendulum. And if I take the datum as this x axis, I have taken this as the datum. From there I measure potential energy, and that happens to be in this form, mg minus r cos omega t, which is this projection, and minus L cos theta, which is this projection. Therefore, we get this height mg, this height h. Therefore, our Lagrangian is kinetic energy minus the potential energy, note the signs. With this Lagrangian, we now start writing out the various terms in the Lagrange's equation of motion. First thing I deal with is del L del theta dot. We have two contributions. Then d dt of del L del theta dot, you will find that now we have explicit time dependence and theta, which is a function of time. So, there will be contributions from all those things, and here there is a double derivative, and here there is this term. Del L del theta, there are two contributions. We calculate partially differentiate the Lagrangian with respect to theta and obtain this, and equation of motion is nothing but d dt of del L del theta dot minus del L del theta is equal to 0, and that gives us this equation of motion. Of course, you can simplify it a little more. Now, this equation you can note has this contribution that comes from the rotating disc. These two terms are for the pendulum, these are standard terms in the pendulum equation, and the intermediate term comes because of the rotation of the disc. We move to the next example. This is equation of motion of a bead sliding on a uniformly rotating circular hoop. This is sliding frictionlessly, and this hoop is rotating at a constant angular speed. I have also drawn the top view of this hoop and shown which angle is omega t, capital omega t. This capital omega t is measured from the x axis. Now, the generalized coordinate, only theta is the generalized coordinate. This example we have seen before, and the Lagrange's equation of motion is also shown here. The Lagrangian is kinetic energy minus potential energy of the system. Kinetic energy of the system is 1/2 mass of the bead times velocity of the bead square. Once again, I write down the position vector of the bead r m, and using standard geometry I can represent the x coordinate, y coordinate and z coordinate. So, I project the position of the bead on this line and take projections on the x axis and y axis. So, this is x this is y, and when I take its this height, so that gives me the, I can take this height, that gives me the z coordinate. This depth, that gives me the z coordinate. Z coordinate is minus r cosine theta k cap. So, theta is being measured like this. If I know the position vector of the bead, I can find out the velocity of the bead. I take time derivatives of all the terms. Remember that x, y, z coordinate system is fixed. It is fixed, there is no frame derivative. I cap, j cap, k cap are fixed in space, they are not moving. I have the velocity vector, therefore, I can find out the magnitude of the velocity vector square, and hence I can find out the kinetic energy of the system. This is the total kinetic energy of the system, which is basically the kinetic energy of the bead. Potential energy system is straightforward, it is in a uniform gravitational field minus mgr cosine theta. The datum is the xy plane. The Lagrangian therefore is the kinetic energy of the system minus potential energy of the system, which is of this form. Now, I start writing out the various terms, del L del q dot and ddt of that I have written out, del L del theta. So, basically q is nothing but theta, generalized coordinate is theta, and del L del theta, and therefore, the equation of motion is ddt of del L del q theta dot minus del L del theta equal to 0, and this is the equation of motion. Which we can simplify. You can see once again there is a pendulum like two terms which correspond to the pendulum equation, and one intermediate term which is because of the hoop's rotation. Just to summarize, we have looked at Hamilton's principle and derived the Lagrange's equation of motion previously, and in this lecture we have looked at some examples in which I have shown the application of Lagrange's equation of motion in various mechanical systems. You have to remember the steps. You have to first identify the generalized coordinate or coordinates, write down the form of Lagrange's equation of motion for individual coordinate, and then express the Lagrangian, which is the kinetic energy of the system minus potential energy of the system in terms of the generalized coordinates and their rates, and then calculate the various terms of the Lagrange's equation of motion, and finally derive the equation of motion. So, with that I will close this lecture.